Hello, I'm Seema. Welcome to my chemistry lessons. The topic of this video is the energy of atomic orbitals. In the case of hydrogen, which has only one electron and one proton in the nucleus attracts that one electron, and that electron may jump from one energy level to the next energy level, but the charge of the nucleus remains constant, and the electron may jump up to any shell. It still the further away the electron goes from the nucleus, the lesser attraction it feels. And that is the reason why the one electron in hydrogen prefers to stay in the lowest energy level, which is closest to the nucleus. Or it stays in the first shell. And the quantum number for the first shell, n, has a value of 1. And since the first shell has only one orbital, that is the s orbital, the electron in hydrogen usually occupies the 1s orbital. When you provide energy to a hydrogen atom, the electron may get excited and it may move on to higher energy levels. It may move to the second shell, the third shell, it may move to any orbital, the 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f. But we notice that when hydrogen jumps to these other levels, the energies of the second level of all the orbitals remains the same. In other words, the energy of the hydrogen electron depends on the principal quantum number, that is, which shell is it in. It does not depend on whether it's on the subshell. It does not change with the subshell. So when hydrogen jumps from 1s to 3p or from 1s to 3d, the energy of the electron in 3p or 3d remains the same. Such orbitals which have the same energy, for example, here in the case of hydrogen, this is 1s, 2s and 2p have the same energy. So these are called degenerate orbitals. Orbitals having the same energy are known as degenerate orbitals. So in the case of hydrogen, 3s, 3p, 3d, all the orbitals of the third shell have the same energy, or they are degenerate. Alright? 4s, 4p, 4d, 4f are also degenerate. But when we move ahead from hydrogen and move on to multi-electron atoms, the dynamics change. Now the nucleus has more protons and therefore the nucleus has a stronger attraction for the electrons. At the same time, whatever is the number of protons is the number of electrons in a neutral atom. So these electrons also have a part to play in the dynamics. These electrons are attracted. The attraction of the nucleus has increased definitely, but these electrons, they start interacting with each other too. And when they interact with each other, they start affecting the charge of the nucleus. So an electron, although the nuclear charge has increased, an electron does not experience the actual nuclear charge, it experiences an effective nuclear charge. Let me explain what I mean by this. The nucleus has protons, that is positive charge, which is attracting the electrons. Let us say on a day the sun is scorching, it's really very hot. So what do you do when you're out in the scorching sun? You try to shield your eyes. By covering your eyes a little, you can see everything because the light of the sun is still there, but the effect of the sun on your pupils may be felt less. So it is less effective. Although the charge is the same, the charge has not changed, but what is effective is different. So what happens when you have electrons in different shells and in different orbitals? An electron which is on the outer side experiences lesser charge from the nucleus due to the presence of other electrons on the inside. It is as if you have this is the nucleus and this is an electron. The nucleus has its charge, is attracting the electron, and although the electron is not so big, I'm just taking an example. And the nucleus, we know, is extremely small, so is the electron. Now an electron which is here away in the next shell, this may be the first shell, an electron which is in the second shell or in another orbital is now being shielded by this electron. So do you think the attraction being experienced by this electron would be the same as the attraction being experienced by this? 1, it is closer to the nucleus. 2, it is screening it. It is screening the effect or the attraction of the nucleus for the outer electron. This is known as the shielding effect or the screening effect. And as a result of this shielding or screening effect, the electrons do not experience the actual charge of the nucleus, rather they experience an effective nuclear charge. So the effective nuclear charge and the actual charge may be different, and one factor that affects this effective nuclear charge is the presence, the shielding effect. The other thing is the interaction between the electrons themselves too, the repulsion that they experience. Now what do we see? The shielding effect of the s orbitals, p orbitals and d orbitals, is it the same? S orbitals are spherical. P orbitals are the shapes of dumbbells. Therefore, an s orbital is spherical and is very compact. It's the smallest orbital in a subshell. That, since it is closer to the nucleus, it will have a more effective screening effect because it is closer and it has chances of electrons all over in the sphere. But a p orbital can screen only along one of the axes. If it's along the x-axis, it will show screening effect only in the x-axis. If it's along the y-axis, it is showing screening effect only in the y-axis or in the z-axis. The d orbitals, on the other hand, they are still more diffused in their shape. They have a double dumbbell shape. And this double dumbbell is like a clover leaf, and since it's diffused, the direction, the effective nuclear charge would still be, it would not be able to screen so well. So screening effect of s orbitals is more than the p orbitals, which is more than the d orbitals, which is still more than the f orbitals, which are still more diffused. So that was about the shielding effect. So now, what decides the energies of these orbitals? Are all the orbitals present in a shell, do they have the same energy? No. This screening effect, since it is different for s orbitals, different for p orbitals, the experience is also different. And as a result of this, these orbitals, the subshells, they develop a difference in their energies. They do not remain degenerate. That is, 3s, 3p and 3d are no longer degenerate. 3s has different energy from 3p, which has different energy from 3d. But remember, the 3 orbitals in p subshell, all of them in one subshell are always degenerate. All the 5d orbitals of any one subshell would always be degenerate. The 7f orbitals would be degenerate, but they will have energy different from the other subshells in the same energy level. As a result of this, we now need some way to find out how does the energy change, how does the energy increase in these orbitals. For polyelectronic atoms or atoms which have more than one electron, it was found that the sum of the principal quantum number and the azimuthal quantum number, they decide the energy of an orbital. The higher the higher the sum, the more will be the energy of the orbital. But if you find the sum of two orbitals to be the same, like we'll see here, 1s orbital, the value of n for 1s orbital is 1, L, that is azimuthal quantum number for s orbitals, is 0, so 1 plus 0 is 1. 2s is 2 plus 0 is 2. Therefore, the energy of 2s orbital should be more than the 1s orbital. 2p would be, sorry, I have written the wrong number here. 2p would be 2 and 1. The principal quantum number is 2 and azimuthal quantum number is 1. So the sum is 3. And 3s is 3 and 0, but this is also 3. So when you have the same sum, then what decides the energy? when the n plus L values are the same for an orbital or the subshell, then the one that has a lower value of n has lower energy. That is how we decide, and that is how it actually is. The principal quantum number, the one that has smaller number of principal quantum number, would have lower energy if the sum of n plus L is the same. So we find that these two have n plus L values are the same, 2p and 3s have the same n plus L values, but n is 2 and here n is 3. Therefore 2p will have lower energy than 2p. Similarly, 3p and 4s both have n plus L values 4, but 3p will have lower energy than 4s because 3 has the principal quantum number 3 and 4s has principal quantum number 4. Similarly, 3d now take a look here. The third shell has d orbitals and the fourth shell has s orbitals. The s orbital of the fourth shell has n plus L value of 4, but the third d orbitals of the third shell have n plus value of 5. N plus L value is 5. Since the n plus L value of 3d orbitals is greater than the n plus L value of 4s, although the principal quantum number is larger, therefore 3d has more energy than the 4s orbitals. So ultimately, you have to find out the sum of n plus L values and decide which orbitals or which subshell has greater energy. But if they have the same value, then the one which has a lower number of principal quantum number would have lower energy.